Excellent. So, like you said, I'm Jim. I'm going to start my talk by trying to argue that fully synchronous coupling is possibly the future of ice shelf ocean modelling. And as anyone who starts to talk with a question, the answer will be yes. So, what I should also probably start with, what is the main problem we face with ice-ocean interactions? That could be argued that everything is linked with everything else. So it's very hard to separate just one system and look what's going on there. For instance, trying to model an ice shelf, what do you actually need to do that? Well, you want to look at the ice shelf cavity, that might be something we want to do. So we might start off very simply thinking, let's have an ocean model and an ice shelf model. And that's a good two-coupled system. You might think that's everyone's seen this kind of picture here. That's the fairly standard system that is used. So you have an ocean model, you have an ice shelf model, there's some coupling between the two, melting, freezing, changing of the boundaries of the ice shelf, all those kind of feedback loops. That's very nice, but you've also got to think what are the boundary conditions for that model? So should that coupled model be in turn coupled to something bigger? I mean, the atmosphere drives an awful lot of conditions for sea ice and things. There's the ice stream further up, how that flows out affects things, and at some point you're going to end up with a coupled model even bigger than all of this, and you can end up with just the Earth, which, while it's very accurate at a one-to-one scale, is possibly slightly impractical to solve any models. I mean, clearly some compromise is going to be needed somewhere for a coupled model. I'm now going to go into what I mean by synchronous and asynchronous. So we start off early models of kind of asynchronous coupling. As in, you run your ocean model, you get a melt rate, you use that melt rate in a separate ice model, you apply that, and wow, 15 seconds is shorter than I thought. Anyway, you apply that, then you restart your ocean model, and there's kind of a disconnect in this synchronicity type thing when you're doing an asynchronous model. Because your models aren't evolving directly in step with one another, there's a possible loss of information. But if we go for synchronous coupling, which is a wonderful new thing to do, we can have that, like I said, in this particular case, the ice-ocean boundary evolving every single time step perfectly in sync. No loss of data whatsoever, which is a much better way to do it. And I'm going to argue why this is a good thing. Like I said, you're not losing any data between time steps as you're evolving your model, which is very good. And in the case of, like I said, our ice shelf ocean thing, if there's some delay between how often you change the size of the cavity and not, then that could be an issue. I mean, you could end up talking about one thing or something else happens. That just would not be good whatsoever. But, however, there are, of course, some downsides to this wonderful synchronized coupling world I'm babbling on about. It is very computationally expensive. And of course, different timescales of, say, an ocean model, typical like 10-minute time step with an ice sheet model of maybe even 6 months, a year. That could be common. But good news, computers are getting more powerful. So, at some point, even though it is ridiculously computationally expensive, we will be able to do this. I mean, maybe not the whole Earth, but definitely it's getting more practical to kind of couple more and more models together. And we can use these to answer what I think is the possibly biggest and easiest sell to try and get funding question in isolation interaction, which is sea level rise, because that's what people care about. And kind of to answer sea level rise, something we really need to know about is what's happening at ice shelves, being the link between the ice on land and the ocean. And a coupled model is a very good way to do this, because there's an awful lot of feedbacks between the ocean and the ice shelf. Like if you melt more of the ice, that's going to affect the size of the cavity, which again affects the dynamics of the ocean and how they feed back on one another. So clearly a coupled synchronous model is a good way of doing this. And we advance. Oh, it's advanced more here. Sorry, so yes. And how I see models advancing in the future. I missed an entire slide. God, this is tough. More and more different models will become coupled as I see in the future. It's not just going to be the cryosphere. At some point, you're going to start adding more things like, we've talked previously about El Niño and La Niña. I mean, adding those kind of things in might be something you want to do. A coupled model is a good way of doing that. So, having said it's a good idea, by a strange coincidence, I myself have been developing a ice shelf ocean coupled model, and in a shameless plug for my poster, you should come and see that in about 30 seconds, I guess. And that leaves me with just one final slide, where I tried to fit all this into 15 seconds per slide. You guys now will have 15 seconds of questions. If you can make them one-word answers, that might go a bit better. So, any questions?
We've got 5 more seconds.
Is it
education expensive?
No.